Hello and welcome everyone to today's webinar, Attaining Proficiency in Industrial Pressure Measurements. This topic will discuss the basics of physics of pressure, the types of pressure sensors, sensor technology comparisons, installation considerations, operation and calibration best practices, and advanced pressure applications. We'd also like to invite you to our upcoming Users Conference. Our next Users Conference will be August 31st through September 3rd in The Woodlands, Texas. It's going to be a great event. There's going to be hundreds of people there, lots of different sessions, lots of networking events, and everybody's going to have a great time. We'd encourage you to come along. You can find out more by visiting YokogawaUsersConference.com. In fact, right now, if you register, you'll be able to save 25% with the early bird special. So we'd invite you to take a look at that. At this moment, we'd like to introduce today's presenters. So first of all, my name is Josh Perry, and I'll be your host. Our first presenter is Michael Keller. And Michael Keller has been with Yokogawa for 7 years. Currently, he's the Field Application Sales Specialist. Previously, he's held positions in product management, application engineering, and worked with a variety of pressure products. Michael has a BS in engineering from the Georgia Institute of Technology. We also have Jason Pittman with us, and Jason is a field application sales specialist in the Midwest region. He has over 11 years of experience, and he has experience in petrochemical, pharma, food and beverage, water and wastewater, chemical blending, petrochemical, and process piping. Jason has a BS in communication from Bradley University. Again, welcome. And with that, we'll go ahead and turn the time over to Jason. Jason, over to you.
Thanks, Josh. Good morning. So pressure, as we know, is one of the 4 common plant measurements, and the others are being temperature, flow, and level, but pressure is the most fundamental and common. Pressure basically is just the amount of force exerted over the unit of area. So mathematically expressed as pressure equal over force over area. And this force may be exerted either by liquids, gas, or solids. Taking a look at the 4 types of pressure, gauge is relative to atmospheric pressure. So gauge has a positive reading for pressures above atmospheric and a negative below. These types of transmitters use a small reference port to obtain an atmospheric reference pressure. Absolute pressure uses a perfect vacuum, so an absolute 0 as its reference. These measurements are always a positive. So absolute pressure transmitters are not affected by any change of local atmospheric pressures. The vacuum is a pressure between atmospheric pressure and an absolute 0 pressure. And then finally, differential measurements take 2 different pressures. The DP transmitter uses a reference port called the low side and compares it to a high side pressure to give you a reading. As you can see, Yokogawa has 3 different offerings here on the pressure transmitter side. We do an absolute, a DP, as well as a gauge pressure. What you're seeing here is we've got the inline mount as well as more of a traditional mount. Taking a quick look at the traditional mount transmitter, you can see that we isolate the sensor from any kind of process temperature or process pressure. This allows for the high and low side to push on the diaphragm as a fill fluid then is pushed through the transmitter onto the sensor itself, and in our case puts the 2 H bars, 1 in tension and 1 in compression, and we'll talk about that a little bit more. So when we take a look at pressure sensor types, there's 3 that we typically talk about. Our capacitance, our piezoresistive, which are both passive sensors, as well as the silicone resin sensor, which is an active sensor. So a capacitant pressure sensor basically is just a large capacitor formed by 1 fixed plate and 1 movable plate, linked to a mechanical output of a diaphragm via a fill fluid. So between these plates is a dielectric material. When the capacitor is energized, changes in pressure at the process diaphragm are hydraulically transferred to the movable plate, causing the distance between the plates to change. This change in distance changes the capacitance between those plates. And so the capacitance detector circuit senses those changes, and the circuitry in the sensor is characterized to know that Y change in the capacitance equals the X change in pressure. Now the output signal from these type of sensors is small and analog. Being an analog signal, an A to D converter must be used to convert the signal to a digital format for the transmitter to process it. So when we look at piezoresistive next, that is based basically on the piezoresistive effect, that the resistance of the semiconductor changes as the mechanical stress changes. So the mechanical stress is caused by process pressure changes, and during that operation, those changes in pressure at that process diaphragm are hydraulically transferred via that fill fluid, similar to the capacitance, to a sensor diaphragm. The circuitry in the sensor is characterized to know that the Y change again is in the resistance is equal to the X change in the pressure. Although there are small types of semiconductors that can be used, typically a single crystal silicone is most widely used. So these sensors use 4 piezoresistors that are connected to form a Wheatstone bridge to maximize the output of the sensor and to reduce sensitivity errors. The output signal from this type of sensor is also analog, so an ADD converter must be used to convert the signal to that digital format. Now we get to the silicone resonant sensor. These are fabricated from a single crystal silicon using a 3D semiconductor micromachining technique. So we've got 2 H-shaped resonators that are patterned on the sensor, each operating at a high frequency output. As pressure is applied, the bridges are simultaneously stressed, and one in compression and one in tension. The resulting change in the resonant frequency produces a high differential output. So this is directly proportional to the applied pressure. This simple time-based function is managed by a microprocessor, and that microprocessor can receive the digital signal directly from the sensor without having to go through an A to D converter. This improves the overall accuracy of the transmitter, since even though it's small, there is a certain probability for error for each stage of conversion. In a DP application, this microprocessor can also use the 2 frequencies to determine not only the differential pressure, but the static pressure. So therefore, this sensor can measure 2 different process attributes with a single sensor. Taking a brief overview of Yokogawa's pressure transmitter history, you can see we've been doing it for about 50 years. Back in the 60s, we started off with just a simple DP cell, moved on to capacitance, and then over to piezoresistive. Then in the 90s, the silicone resonance sensor was developed. And about 94, it was introduced to the North America market in the EJA A series transmitter. About 2004, the EJXA was developed. This allowed for better accuracy, quicker response time, more long-term stability of the transmitter. And then about 2012, the EJA E series, which was basically a revision or upgrade to the EJA A, was developed. This allowed for a quicker response time, some of the more features and benefits that the EJXA also has. So today, both the EJXA and the EJAE are available to our customers. Just looking at a quick comparison between the 3 different types of sensors, you can see the advantages on the capacitance. They're very reliable on low and vacuum pressure applications, very mature design. Disadvantages there, they're electronically complex to make. They typically and only measure one process variable, require the ADD converter, low signal to noise. They have a poor overpressure handling capability, and again, as we mentioned before, they are a passive sensor. Piezoresistive, quick response time, and easy to manufacture. The problems with this, again, is the measures only one process variable and doesn't do well with large temperature effect. AD converter is needed, and the overpressurization is poor, again, like the capacitance because of the passive sensor and some of the design of that sensor. When we look at the silicone resonant, as I mentioned before, it's an active sensor, very stable, repeatable output, a true digital signal, high signal to noise ratio, high accuracy and predictable, and it's a multi-sensing sensor. The one downside is relatively complex to manufacture. So just taking a quick look again at the silicone resonant sensor technology itself and how it's multi-sensing. I mentioned Yokogawa's DP harp can measure both differential pressure and static pressure with one transmitter. So the silicone resonant sensors I mentioned before are fabricated with the single crystal silicone. So these H-shaped resonators are patterned on that sensor, each operating at a high frequency output. So as the pressure is applied, the bridges are simultaneously stressed, one in compression and one in tension. The difference between those 2 frequencies is proportional to that differential pressure, and the addition of those 2 frequencies is proportional to the static pressure. So in addition, the sensor has a natural thermocouple between the 2 dissimilar metals in the sensor's construction. This allows the sensor to measure a temperature within itself, The transmitter uses the static pressure measurements and the temperature measurement to perform a dynamic compensation, which allows for corrections and process changes in real time. And Michael will speak more on that here in just a minute. With that, I'm going to turn it over to Michael to talk about some of the transmitter performances and calibration.
All right, thanks, Jason. So we'll get right into it. So we'll talk about specifically, yeah, there's all these sensor types, that's great, but what does that mean to a performance of a transmitter? So what's the real world performance? So all manufacturers of pressure transmitters, they all have what we call reference accuracy, and usually that's getting to pretty crazy tolerances. So 0.05% of span, 0.04% of span, even 0.025% of span. We're getting down to the real nitty gritty, almost to where it's difficult to verify. So again, the laboratory accuracy, under a controlled environment, not really what these transmitters are going to be installed in. So really, these transmitters are typically in plant environments that are outside. They're going to have swinging temperatures from day to night, summer to winter. The process that they're measuring, that temperature will change. Static pressure will change as well, depending on the application. If you're measuring differential pressure, that static pressure within the vessel or line might change. And then we have what's called overpressure effect, which I'll talk about in a little bit more detail, but that can drastically affect the performance of your transmitter in these real world conditions. All right, so what does that real world performance means? How can we quantify that? So we have a definition Yokogawa's come up with called total accuracy. So basically it takes into all those considerations, basically that reference accuracy, because that is a big part, that's what we calibrate to, but also accounting for ambient and process temperature changes, static pressure changes, whether it's changing in the vessel, what have you, and then that overpressure effect, which I'll talk about specifically how that can affect your measurement. But this is a real definition of how we can really judge the performance of a transmitter in your applications. So one thing all manufacturers do, or Yokogawa does with every capsule to establish this real-world performance, is we characterize each transmitter. So we characterize each capsule. They're all a little bit different. So we have basically a curve set up to say, hey, if you're reading zero pressure, we want to make sure we're outputting zero pressure. Whatever the capsule max range is, if you're reading that max 100%, we want to make sure we're outputting that 100%, and we're as linear as possible along that curve. So even if you make the range 0 to 10%, 0 to 5%, we still want to make sure through this characterization that we're always measuring accurately what that pressure is truly going to be. So we characterize each capsule to ensure that along its whole measurement range, it's always accurate. So also with our silicon resonant sensor, we have, like Jason talked about, that multi-sensing technique, and where that really comes into play is for this characterization, this compensation. So we're always reading static pressure, we're always reading temperature, and we're taking those values and we're compensating for those effects. So we're able to limit the performance loss because of that, to make sure we have that, again, that good total real-world performance accuracy.
Okay, so silicone resonant, we're talking about overpressurization. We talked about that a little bit ago, comparing to the passive sensors. Well, Yokogawa here on our overpressurization, we always run a spec that we can handle overpressurization and come back within plus or minus 0.03% of the upper range limit. And how we do this is basically mechanically within that traditional mount. You can see that we've got a high and low side on the diaphragms themselves, but in essence there are two small diaphragms inside as well that you see highlighted in the dark blue area. And if you happen to have an overpressurization event, as the fill fluid is pushed up through one of the capillaries, let's take a look at the blue side, it goes to the right and then up. You see a small little leg that kicks off to the right. That allows for that fill fluid then to dump into the other side and protects the pressure sensor itself from any kind of overpressurization. When that event then is over and the pressure has subsided, then that fill fluid then goes back to the other side, and then your transmitter itself will come back into its normal operating within that plus or minus 0.03%. And then you don't necessarily have to concern yourself with any kind of damage to your sensor at that point. Now, not many people can do this. I don't think anybody other than Yokogawa can, but this is one of our very big features on our traditional mount.
Okay, perfect. Yeah, great. Okay. So again, yeah, that overpressure effect, real critical. You can have applications that, if you have like a common one's drum level in a power plant, so you might have real high static pressures, maybe 1,000 psi in each side of a DP transmitter, but you're trying to measure a real low differential, let's say 20 inches of water. So if you have a situation where somebody sequences a manifold wrong, or during startup conditions, water hammer effect, there can be a lot of issues or conditions where you hit one side of the transmitter with a way too high of pressure, way too high differential, and you don't realize it, and it could damage the sensor or cause the calibration to be off. So having that overpressure protection is critical to protect from those conditions. So with all that, with this total accuracy, with the overpressure, we have the means of calculating calibration intervals. So, most plants, they might have a set standard. They calibrate every transmitter every 1 year, every 2 years. But with this information, this total accuracy, and a specification we call long-term stability, which accounts for the long-term performance of the transmitter, the degradation of components, we actually can take all this info, and using our specs, we can actually, if you tell us you need a 1% device, a 0.5% device, we can actually give you details on what your calibration interval could be based on guaranteed specifications that we have. So we've had a large power company go to our EJX transmitter just because of the cost savings of having this extended calibration intervals. If you think about total cost of ownership, if you can buy a transmitter that's going to extend your calibration interval a couple of years, if you've got 100 transmitters in your plant, you only have to, every calibration roughly might cost $100 with equipment and manpower and all that. So that's significant cost savings if you can kind of adjust those intervals by going to a higher performance transmitter. So with that short little, I guess, good audio, I'm going to flip it back to Jason to talk a little bit about installation conditions or considerations.
Okay, so just as a kind of a brief overview of some installation techniques, obviously first and foremost, we're always going to refer you to the installation manual for proper piping of impulse lines. But just a quickly kind of overview, obviously the impulse lines are there to transfer that pressure from the process to the transmitter, also to protect the transmitter then from that process as well. So starting on the left, you can see a typical gas application where we're mounting the transmitter above the piping. This allows for any kind of liquid to drain away from the transmitter, so it's getting a nice, accurate, stable reading. On the liquid side, as well as steam, you're seeing that we're putting the transmitter below. This will ensure that those impulse lines are nice and full with liquid. It allows any entrapped air to go back up the impulse lines and into the process pipe to the top of the pipe, and give us an accurate and stable reading as well. On the steam side, we're always going to recommend that you fill those impulse lines with water. Again, this just gives you a nice, stable, steady reading. It doesn't allow any kind of drifting on the transmitter. So you can see on the right, the Yokogawa transmitters, we offer a universal mount. This can allow you to mount your transmitter in either horizontal or a vertical orientation. This is a great solution if you are determining that you want to stock some of the transmitters. You're not really sure where and when they're going to be used, so you don't have to order a specific mounting style for the transmitter and then be stuck if you don't have the right one the time that you need one. So this is just a typical installation that you might see for a level on a tank. You can see your high and low side there, top and bottom, and then your impulse lines over to the transmitter. Keep in mind when you do this installation, we also have an auto leveling function in there. This will allow you to not have to do all the fun math and enter in all those numbers by hand. Looking at manifolds as well and instrumentation, we obviously typically will always recommend a manifold. You've got a 2, 3, or 5 valve type that's available. This is a great way to isolate the transmitter from the process, allows for some venting. Again, this will reduce the number of leak points. And then this also enables for some on-site calibration and ease of zeroing of a transmitter. Just a closer look at some of those manifold body styles. You can see on the left we've got the single flange, which is NPT on one side, and then flanged for the transmitter. The remote or inline that is installed on a pipe there. Your typical block and bleed, which is the threaded unit there, just to isolate, say, a gauge pressure. Double flange, flanged each side, and then finally the coplanar manifold. And Michael will then talk to you a little bit about some configuration and programming.
So typically, with most transmitter manufacturers, they'll provide some type of configuration or setup of the instrument before you get it at no charge or maybe for a small fee. So generally, for a pressure transmitter, what you're going to want to include is that calibration range in units. So you can have it specified to the max range of whatever capsule, but also if you want to have it calibrated to your specific calibration range for your application, we can do that as well. The output, so whether it's linear or square root, so we'll talk a little bit later about differential pressure flow, but typically you want to square root that output for that. So sometimes that can be done in your control system, or you can do it at the transmitter as well. But also if you want to put flow, have flow units on your display, you want to square root that, and that might be independent of your output depending on where you square root either the DCS or the transmitter itself. Same thing with display scale and units. It might be different from the actual pressure scale if you're measuring level, if you're measuring flow. And then depending on the type of output, Hart's probably the most common in the industry. You can select Hart 5 or 7, depending on what control system or what devices, handhelds you can talk to. You just need to know what revision of Hart is preferable. The tag number, so this is the physical tag that is going to be engraved on the neck or possibly on a wired-on tag on the transmitter. And then there's also a software tag, that's the identifier electronically. So in terms of programming for Yokogawa instruments, we do have a series of field guides that are very good, kind of talking to specific things in terms of the setup or features of our pressure transmitters. So just to talk briefly about a couple of these. So we have one about the indicator itself, setting it up for flow units or square root or level, anything like that, just showing all the functionalities. We have what's called a local parameter setting. So if you don't have a Hart handheld or a device configurator, there actually is capability with a button on the display and a screwdriver for setting up the common features of a pressure transmitter. Signal characterization, so if you have a non-uniform geometry tank, you can do some adjustments in the output to kind of make sure your level measurement's correct. And then bidirectional flow, if you have an application with an element, some type of differential pressure device, you can actually do bidirectional square root to make sure you're outputting correctly on the transmitter to correspond with flow. So these are all available on the website. And now let's talk specifically about calibration. Again, we talked about extending those calibration intervals, but at some point you do have to calibrate these devices and verify them. So we'll talk about specifically, what a typical calibration procedure is on a pressure transmitter. So our recommendation from our, instruction manuals, we say warm up the unit for at least 5 minutes. And 10 minutes for actually absolute pressure transmitters. So that's something we recommend. Maybe it's not possible with your specific application, but that's the official Yokogawa recommendation. The diagram on the left kind of shows the equipment required. Basically, you've got some type of pressure generator that's also referencing or measuring pressure. And typically, you want that to be at least 4 times as accurate as the transmitter you're measuring. So if you've got a 0.04% reference accuracy transmitter, you need a 0.01% calibrator to be able to verify the performance of that transmitter. So that's something to always keep in mind. And then you're using some type of device to measure that output and make sure it corresponds to the pressure being supplied. So depending on your range, if you have a suppressed zero or the zero shifted in the positive direction, you can have this configuration where you're supplying pressure to the high side. If you have a elevated zero or the 0 points shift in the negative direction, you want to use the same configuration, but that reference pressure should be using a vacuum pump. So typical calibration, we recommend a 5 points. So whatever your range is for your application, you go to 0%, 50%, 100%, and then back down to 50% and 0%, just to verify there's no hysteresis, there's no change when you're bringing it back down after you've pressurized it. So this is a typical 5-point calibration. You can also do a 9-point, which is even more thorough, throwing in 25% and 75% as data points. So at each point, you're going to calculate the errors, so the difference between that output you're reading from the transmitter and your pressure reference, and make sure the errors are within the tolerance of your required accuracy. And hopefully, everything's good, as left as found, you don't have to adjust anything. But if you do find that it is off at various points, we have some means of trimming these transmitters, sensor trim, and trimming the analog output, which I'll go into a little bit of detail on how to do that. So a zero trim is just a 1-point adjustment, usually to account for mounting position effects. We'll talk about, remote seals. Typically, you're going to have head pressure effects. Any transmitter really, if you put it in, on a bracket in its installation with tubing, it's going to have a little bit of head pressure. So you're going to always want to zero that out under typically process conditions. So that's a common practice. So you're always going to want to zero your transmitter right when it's installed. Full sensor trim, again, is this process when you do your calibration and you find at various points the accuracy is not correct. So we provide a 2-point process. So you basically trim the transmitter at 0% and 100%, and it's linear in between. So you're making that adjustment. You've got to make sure, based on your calibration, that you fit that line basically between all the points where you verified the accuracy. So we have a functionality in our transmitter, this auto sensor trim. So if you can supply 0% and 100% of your application, you can basically tell the transmitter what you want it to read, and it'll adjust it automatically. So if you've got a calibrator, you're supplying 0 inches of water, the transmitter's reading a 1/2 inch, you just tell the transmitter, hey, I want you to read 0, plug that in, and it'll adjust accordingly. Same thing, if the top end of the application is 100 inches of water, if it's reading 102 inches of water, you just tell it you want it to read 100, and it'll automatically make that adjustment. And you always want to do that lower point first, just because if you do the upper point first, it's going to affect that lower point adjustment. So always do the 0 trim before you do a full scale trim. And then a D to A trim. So this isn't meant for adjusting for calibration, but just fine tuning, common 4 to 20 output. So if it's reading a little bit off in terms of milliamps, you can make that adjustment with the D to A trim. And one really nice feature on all Yokogawa transmitters, so you can always reset the trim back to factory settings. So there's a clear pressure sensor trim command in Heart, and also the same for static pressure. So you can clear everything out back to factory settings if you make a mistake. A common one's like an absolute pressure transmitter. Again, like Jason talked about, you're referencing that at 0 absolute pressure is what it's being referenced. But if you zero that transmitter at atmospheric pressure, you've effectively turned it into a gauge, and you really need to clear that trim to get it back to an absolute measurement. And just what I talked about is kind of showed in a little more detail in one of our field guides, this sensor trim that's available on our website. So it walks you through step by step and actually talks about a specific level application as well, where you can basically use a site class and match specifically what the level reading should be. Okay, so I'll pass it over to Jason again, and he's going to talk about a couple pressure applications.
Okay, thank you, appreciate it. So DP flow measurements using the transmitters. So as we know how this flow is measured, it's based on Bernoulli's principle. So the increased fluid velocity results in decreased pressure. So the differential pressure across a known geometry or a primary element, that causes that loss in pressure, and that is proportional to the flow. So typically when you're setting up this type of application, the simple components that are going to always be needed is your primary element, whether it's an orifice plate or venturi or some other type of meter. Your impulse lines, which are running down to your secondary element, which is your DP transmitter. So some additional items that can be used if you're looking to dial in a little bit more on some dynamic compensation. Keep in mind that the silicone resonant sensor dynamically compensates with the static pressure and temperature in there as well. But if there are some additional items needed, you could use a gauge or absolute pressure transmitter and a flow computer for configuring all that, or possibly a gas chromatograph. This also gives us the ability to have a better accurate and more reliable reading. So looking at just the simple principles of operations using a primary element. So the differential flow meter, whether it's a venturi tube, flow nozzle, or an orifice plate, these are all inline instruments that are installed between two pipe flanges. So you've got pressure taps, as you can see on this picture on the bottom, and these are added to either side of that orifice plate in this case. As the velocity of the fluid leaving the orifice is greater than the velocity of the fluid entering the orifice, we're going to apply that Bernoulli's principle, and that increased fluid velocity results in the decrease in pressure. So as that fluid flow rate increases through the pipe, back pressure on the incoming side increases due to the restriction of the flow created by the orifice plate, and the pressure of the fluid at the downstream side of the plate is less than the incoming side due to acceleration and flow. So with that known differential pressure and the velocity of the fluid, the volumetric flow can be determined. So here's where you'd see you've got your P1 and P2, you'd have your impulse lines, and then you'd have your transmitter running down to that. So it's a little bit of an eye chart, but you can see there's a number of different primary flow elements. You might be able to read this at a later time if you want to print this up. So you've got a number of different orifice plates, whether it's a center hole in the center, or an eccentrical or a concentrical hole. You've also got the venturi meter in here. And we talk about wedge meters, pitot tubes. So these are just a list of a number of different primary elements that can be used with a pressure transmitter or a DP transmitter to determine flow readings. Looking at a couple quick solutions, Yokogawa has teamed up here with Veris. This is one of our Veris solutions, combining a Varibar and the nozzle. So again, this increases that DP over the standard Varibar and increases the operating range, and especially good in low flow applications. The nice thing about this is gives you limited straight run requirements. So if you've got a tight space, you need to put something in, you've got the availability to do that. We take a look at a multivariable transmitter. So this is a situation where you might have a lot of swing and process conditions, whether it's pressure or temperature. On the left, you can kind of see a traditional setup where you've got a differential pressure transmitter at the bottom, a static pressure, whether it's gauge or absolute, up to the top left, and then a temperature sensor. Historically, these are all then run back to a flow computer, and you're taking a flow computer to determine what that flow rate is of that process. Using a multivariable or a 910 from Yokogawa, being that we are an active sensor and able to sense the static pressure side, we eliminate that gauge or absolute pressure. And we also eliminate the flow computer, being that the multivariable transmitter can take a temperature reading on the downstream side of that orifice plate in this picture and bring that in and do all the calculations to give you a mass flow rate, being that is multi-sensing. Michael's going to talk about some remote diaphragm seals and some of the best practices to kind of close us out today.
Okay, sounds good. Thank you, Jason. All right, so to start with, what's a diaphragm seal? So again, just like our capsule, we've got silicone oil and diaphragms kind of mechanically conveying our pressure to a sensor. This is just kind of a further expansion of that. So we've got our transmitter diaphragm on the left, and then we have an external diaphragm and more hydraulic fluid. Typically it's a silicone oil that's just conveying that force of pressure to the transmitter itself. So why do we do this? What's the point of these diaphragm seals? Why do we attach them to our transmitter? So there's a few kind of common cases. So high temperature applications. Our transmitter can handle 250 Fahrenheit as standard, and that's pretty standard across the industry. So with remote seals, we can up that tolerance all the way up to almost 750 Fahrenheit. For corrosive service, so we can get different wetted materials with these remote diaphragm seals. So that's a common application. Isolation of the process for safety. So again, we've got this mechanical conveyance. Usually the transmitter can be remote mounted, physically, 10, 20, 30 feet from the process, so we can isolate it. Suspended solids in the process. So again, we're moving from a typical, threaded small NPT connection to a larger flange surface. So that'll help if you have some sticky process or some slurries. Sanitary connections for the food and beverage industry. We can get those with these remote seals. Replacement of wet legs. So these are just impulse line stainless steel tubing that we fill with typically condensate water that can empty and fill and cause issues with your measurement. So having this sealed diaphragm seal system really helps with that. Ease of cleaning between batches, so we can have what are called flushing connections, that you're able to flush out these process connections between batches. And then user safety. So specifically with this, again, we can remote mount that transmitter, get it away from the process, and we do have specific fill fluids that are inert. So like if you have reactive processes, we have a fill fluid that if there was a failure, it wouldn't react with the process and cause any issues for safety. Okay, so just to go over a couple common terms, the diaphragm seal, so kind of shown in the picture in the right, sometimes known, so this is the entire seal assembly. We sometimes call it a remote seal. You might hear chemical seal or isolator. Process wetted, so for these remote seals, that's typically the diaphragm seal components that are all coming directly in contact with the process. So typically for these seals, it's the diaphragm, any lower housing or flushing ring, and any gaskets or O-rings that would be associated with these seals. But there are non-wetted parts on these diaphragm seals. that don't directly come in contact with the process. So there's an upper housing, any assembly hardware, backing flanges. So those might not be need as corrosion resistant materials, but if you have a corrosive atmosphere, you need to consider that as well in terms of process resistance. So the diaphragm itself, this thin, flexible material that's directly contacting the process, sometimes it's called the membrane or the sensing element. You have a system fill fluid, so that's what's behind the diaphragm and going into our pressure transmitter. So again, transferring that pressure from the diaphragm to the instrument. And then a flushing port, this is kind of a spacer in between your process flange and the diaphragm seal that can have connections that you can either calibrate from, sometimes they're called a calibration ring, but also you can flush that process connection if there is buildup or any issues like that. Some other terms, a balance system. So if you have a differential pressure that would have two remote seals equal in length, that's what we call a balance system. That's typically because we can cancel out some of the effects that will happen to remote seals, which I'll get into a little bit more detail. But we can also have an unbalanced system. So you'll have, again, those two remote seals on a DP transmitter, but they're not equal in length. Common situation is you want a direct mount on the high side of the transmitter and then a remote mount capillary in the low side, so you can mount that transmitter, let's say for a level application at the bottom of a tank. And again, we can do some different things in terms of the size of the diaphragms and thickness to kind of account for some installation or some effects that we'll have with this configuration. So one thing always to consider with remote seals is it going to affect the performance of the transmitter. So specifically, it's going to affect response time and it's going to affect the accuracy of the transmitter. So when we talk about that reference accuracy, pressure, temperature effects, all of those are going to be magnified or affected based on the remote seal chosen. And really, there's a lot of things to consider that can affect this. So specifically with response time, the capillary length and the actual diameter of the specific capillary, the fill fluid that you've chosen inside the remote seal, the diaphragm diameter, and then what type of process and ambient temperature swings that you're going to have. So a common case, if your application's up in Canada in winter, if you've got 30 foot of capillary with a fairly viscous fill fluid, your response time can go from 90 milliseconds from our standard transmitter all the way to above a minute. So that's always something to be considerate of when you're choosing remote seals. Same thing on accuracy, so the capillary length, the diameter of that capillary, the seal diaphragm diameter, which I'll talk about a little bit more, how that affects accuracy, and again, that specific fill fluid and how much swing you're going to have on the process and ambient temperatures. So when choosing a fill fluid, what are the best practices? So you got to consider, again, what type of application. Remote seals are common applications level, but again, we measure pressure commonly, and in certain cases, we sometimes do flow with remote seals. Again, you got to make sure when you choose a fill fluid, it can handle the process temperature swing you're expected to see, and also the ambient temperature swing. Certain fill fluids, they might be good at hot process temperatures, but maybe can't handle the low ambient temperatures that the transmitter might see out in the environment they're installed in. Also, you want to consider what type of service you have. So if you're in food and beverage, you probably need a food grade fill fluid. Chemical plants, so if you have, again, that reactive process, you're probably going to want to have something that's inert, so that's not going to affect the process if it did kind of breach and react and get into the process. Same thing with water. You got to make sure, like the food grade, how that'd be affected if there was a breach and got into the application, the process. And then also vacuum. So any vacuum, like if you have a blanketed tank that's seeing vacuum generally with these fill fluids, it kind of encloses the operating temperature ranges. So that's something to be considered of. And as you go deeper into vacuum, usually that temperature envelope of those fill fluids gets smaller and smaller. So that's something you got to always consider. And there are specific fill fluids too that are only meant for vacuum, and others that don't perform well with vacuum. So temperature effects, this is a common issue with remote seals in general. So again, you've got a significant, compared to the transmitter itself, a significant amount, typically with capillaries and the big flanges, of added oil, so added fluid, so that's going to expand and contract with temperature. So this is a sealed system, so as process temperature changes, ambient temperature changes from day to night, summer to winter, that fill fluid is going to expand and contract accordingly, and because it has nowhere to go, it's the only place it can go is the the transmitter itself, so it's going to cause an incorrect reading based on temperature swings. So you can almost trend that and see that effect from day to night, summer to winter, whenever temperature changes. So how we address this typically is we go to larger diaphragms. So usually larger diaphragms they're more forgiving, they're more accommodating, they're less stiff, so they can kind of contain that expansion and contraction without causing an incorrect pressure reading to the transmitter itself. So just showing kind of typical makeup of a transmitter, all the components. You've got a capillary, a seal. But what we specifically want to talk about, again, with those temperature effects, we have the means, Yokogawa, if you give us application data, process temperatures, process pressure, installation lengths between taps on seals, we can take all that information, all that application data into consideration, and we can give you a seal sizing basically to determine whether or not the seal you've chosen is a good choice for your application. But this table on the bottom left is a good kind of rule of thumb. Generally, if you have, again, we want that larger diaphragm for smaller pressure applications because they can get affected more. So generally, if you have a DP application in the inches of water realm, you typically want a diaphragm above 3 inches. If you're measuring gauge pressure, in the PSI realm, you typically want a diaphragm of 2 inches. But again, we're always there to provide additional guidance, but this is just a good kind of rule of thumb going forward. And then Yokogawa seal offering. So this is what we manufacture, what we provide. So we have a couple different options. So we have a direct mount seal. So the EJX and the EJA 210. So it's just a DP transmitter with a direct mount seal on the high side. We have remote seals, the EJA and EJX 118. So that balance system that we talked about. So 2 remote seals on a DP transmitter in equal length to account for those any temperature effects. They'll both hit both sides the same way. Then we do have a remote gauge transmitter, so the EJX and EJA 438. So it's a capillary on a gauge pressure transmitter. And then a new offering, so instead of using like the EJA and EJX 118, doing differential pressure with one transmitter and remote seals, we remove the capillaries and we basically take 2 static pressure transmitters and do the math between them to come up with differential pressure and typically level. This has certain applications where it's good, usually really tall tanks. Again, we want to evaluate each application, but typically if the distance between the taps on your tank is more than 50 feet, this is typically a good measurement. We get rid of some of those temperature effects that can affect the capillaries, but generally below 50 feet, the DP transmitter like the 118 is a better offering. And then outside of this, these products, we can work with our third-party partner, Wyka, to get any other seals, like I talked about sanitary for food and beverage, for pulp and paper, the PMC seal, or just any other offering that we don't have, we can go to Wyka to provide a solution. Okay, in summary, in talking about what we went over today, of course, pressure, there's 3 main types: differential pressure, gauge, and absolute. Everything kind of boils down to that. Again, pressure transmitters are very configurable because they're not just used for pressure, but also flow and level applications commonly. And then just something we didn't really touch on, but every pressure transmitter we talked about today in some configuration is manufactured in our Newnan, Georgia facility. So we've got over 400 people here, and we try to manufacture as much as we can just to support the North American market with quick lead times. Touching on some additional resources that are available on our website, we have a pressure handbook that goes over kind of what we talked about today, specifically pressure measurement and all the things that come with that. And then there's also a video of 10 common pressure transmitter questions that we kind of try to address that we see day to day when we get questions either over the phone or through our people on site. Okay, I think with that, are there any questions?
Thank you. And there's actually several questions coming in. Those of you that still have additional questions, if you could go ahead and submit those through the Q&A area in the lower right-hand corner of your screen. We'll go ahead and get to those now. Also, we apologize for some of the audio issues earlier. Again, we will get you a recording, and within that recording, we'll have the audio in a better fashion, so you'll be able to see and hear some of the things that you might have missed earlier in the presentation. So our first question, and actually let's give this one to Jason as a starting point. Jason, the question is, what are some common transmitter failures that are seen out in the field?
Hey, actually, I'll take that one if that's okay.
Yeah, okay.
Yeah.
That works. Yeah.
Okay. So this is Michael Keller. Just talking about common failures. So again, I cover the southeast for Yokogawa. So I travel all over to various plant sites, and I see a lot of not a lot of Yokogawa failures, but a lot of other transmitter manufacturer failures. But a common one is just like we talked about, overpressure. Again, a lot of applications, maybe they don't realize that this can happen, but it's very common occurrence. Again, like we talked about that boiler drum application, you've got really high static pressures and you're measuring a really low DP. So if one side of the transmitter ever sees that high static pressure, it can really throw off the transmitter. The transmitter's not going to fail physically, but the sensor itself can be damaged or can go out of calibration. So we see that very commonly with high static pressure applications. And then just also temperature, either through misapplication of, again, across the industry, standard transmitters can see 250 Fahrenheit, but we can get extended temperature intervals with the remote seals. A lot of times if, maybe in your process you don't realize what the actual process temperature could get to, just making sure that's correct and choosing the right solution to handle temperature. And then last thing, just in general, wetted materials. We always defer to the customer and choices of wetted materials because they know their process best. But again, we've got a lot of different options that we can offer to make sure we offer a compatible material that you choose for your application. So those are the common failures that I see day to day.
Great. Maybe to add on to that, there's a question that's somewhat related. It says, what wetted materials do you offer for corrosive processes?
So our standard wetted materials on our standard, just either inline or DP transmitters, traditional mount, we have a Hastelloy diaphragm at no upcharge. So that's our bare minimum bare wetted materials. And then everything else is 316 stainless steel. But we can get all Hastelloy, we can do tantalum, we can do Monel, and again, same thing with the seals. So we can always provide an all, depending on the request, we can usually kind of accommodate. There hasn't been many instances where we haven't been able to provide a wetted material.
Okay, great. Here's another one. It says, do Yokogawa transmitters have any advanced diagnostic capabilities?
So I'll grab that one. Sorry about that, Michael. I was having a coughing fit, so I was on mute there. Thanks for taking that. To answer that question, yeah, being the fact that, again, the DP heart's an active sensor, it's always resonating or oscillating, even when it doesn't have any pressure applied. So if you ever have any situation where one or the other resonators fail, or both of them, those transmitters will, diagnose that and capsule error, and it will give you a failure alarm right away, whether it's failing high or low, depending on the transmitter, however you configure it. So this is, inherited to having that active sensor, where on the passive side, you're kind of waiting for something to happen to see if there's been a failure.
Okay, cool. Here's another question. It says, why would you choose the traditional remote seals for differential pressure over electronic differential pressure?
So I'll take that one. So it's just the nature of the measurement. So again, a differential pressure transmitter, it's meant to, we'll talk specifically about, English units, but it's meant typically, like the capsule ranges are meant for inches of water. So that's its natural measurement. With the DRS, these electronic remote seals, they are two static pressure transmitters, which are typically kind of in the realm of PSI gauge pressure. And you're trying to take two transmitters that are more high pressure measurement and measuring the difference between them. So you're taking two accuracies and compounding those errors to try to come up with a measurement. So in general, with limited capillary length, even temperature effects, considering those for the capillaries, we always kind of default to the remote seals. And actually Yokogawa has some unique compensation that basically we can kind of account for ambient temperature changes without allowing any of that drift, any of that offset. So in general, like I said, we want to review every application, but probably, I'm just kind of speaking offhand, but we probably still sell 90% of applications that are DP level with remote seals. We still do the traditional, 118 remote seals. And then for those specialty ones, those really high, tall tanks, That's when we go to our electronic remote seals, where the temperature effects would be so great that, yeah, we can't use the traditional remote seals.
Cool, thank you. All right, here's another one. It says, is there a multivariable transmitter that reads temperature as well as the same sensor/cell?
Yeah, I'll take that one. So like Jason talked about, there's a specific transmitter, the EJX 910, that again, yeah, with our standard DP transmitters, we can do differential pressure and static pressure, but we don't have process temperature. We have capsule temperature, which is used for compensation, that dynamic compensation, that characterization. But we do have this specialized multivariable transmitter that takes process temperature through an RTD, and then static pressure and differential pressure, and then can do compensated mass flow calculations to give you a true mass flow output.
Okay, great. Here's another question. It says, can you advise if a differential pressure transmitter could be used for a level with high viscous fluid in a vessel or tank?
Yeah, I'll address that one. I mean, really, as long as we've got, like in food and beverage, there are some viscous applications. It's one of these things that we want to get some more details, and we want to provide guidance when we know all the information. But there definitely have been applications with viscous media in a tank that we can use remote seals. It just depends, with again, we got a larger surface area with these remote seals, but we just got to make sure that we're preventing any type of clogging or gunking up on the process measurement. But yeah, if you can contact us via our support or our, through the website, we can maybe talk about that application further.
Awesome, thank you. Okay, here's another one. It says, is the overpressure protection only applicable for DP transmitters or for regular ones too?
I'll grab that one, Michael. Yep. So to answer your question on the overpressurization, that's typically dealing with the traditional mount, or you've got the two diaphragms on either side and that fill fluid. When you're talking more of an inline mount and a gauge pressure, you're overpressurizing. Basically, if you go over the range of that capsule, you're probably not going to overpressurize the entire internals there, so it's going to come back within or come back from an overpressurization event.
Thank you. Okay, here's another one. It says, are there test points to measure the MA output on the back terminal, or is getting in series with a loop a requirement?
Sorry, Josh, I got that one. Yeah, there are check terminals. You use the low side of the 4 to 20 milliamp, but there is a specific check terminal on the terminal block of the transmitter that, yeah, you don't have to break the loop.
Okay, great. Another one says, do other manufacturers use similar technology as Yokogawa?
So I'll take that one. So yeah.
Go ahead.
Oh, sorry, Jason. So yeah, specifically, we've, as Jason pointed out, we've done the capacitive sensor, we've done the piezoresistive, we kind of evolved, but Yokogawa invested $50 million to kind of advance the pressure sensor technology, and we're the only ones currently to come out with a silicon resonant sensor that is truly unique to us, and I think we talked specifically today about the performance benefits of this sensor. That's why we can guarantee our specifications and our long-term performance.
Great, thank you. All right, I think that's all the questions that we're going to get to today. There were a couple others that we'll follow up with you all individually on. We thank you all for taking the time to be here with us. We will be having additional webinars. In fact, there's another one that'll be coming up in December, and we hope to see you on that webinar. Thank you for your participation. Michael and Jason, thank you for your presentation. It was very informative, and we hope to see you all next time.